context of networks, and what are these techniques, how do they compare, and what is the key idea behind them, etc. First, let's see why there's a need for multiplexing. Okay? When we say multiplexing, that means that there are a number of inputs and there are number of outputs. So let's say for simplicity, let's consider one output. So these inputs will be sharing the output link. That means assume that there are data or signal which arrives at each of the input links. Okay, how they are multiplexed onto the output link. In other words, how the output link bandwidth, okay, or capacity is used between the 4 input links here. Okay. Why there's a need for multiplexing? Just imagine a telephone network. I'm talking about the telephone network, which is the true landline telephone network. See, for example, which is managed by, let's say, Singtel. I'm not talking about the telephone network which nowadays we use with the help of broadband, the IP-based telephones. No. I'm talking about the telephone network. Usually the housing premises, you find the telephone socket on the wall, right? So just imagine a telephone network. Let's say there are a number of users. As you know, the users could be in millions nowadays, right? So can we provide connectivity between all possible users? Each telephone connection requires 64 kbps. So I don't have time to explain why we need 64 kbps, okay? That comes from sampling theorem and all, that's fine. Assume that we need 64 kbps transmission and also the communication cable or path for each telephone connection. So can we have all-to-all connection? That means can we connect every user to every other user? Is it possible to provide cables between all possible users? No, it's not possible, right? We cannot directly have direct cables connecting all users or homes, okay? So instead what we can do is we can have a few 64 kbps links which all start from our houses, okay? And we need some kind of multiplexer at some point to aggregate a number of 64 kbps connections onto a single output link. Okay? Then in the next level, we will have another level of multiplexer. Okay? So that way we can reduce the infrastructure cost. Otherwise, we cannot lay out the cables connecting all possible users in a country or city or in the world, right? Okay, so let's start with a very simple multiplexer. Okay, of course, the concept is similar, even if you extend to more inputs, more outputs. Okay? So this is how we represent a multiplexer. So basically, if you take, let's say, network switch or router, that does multiplexing because it receives data from multiple ports, and they also send data or packets to other ports. Okay? So symbolically, we represent like this. The question is, how do we multiplex the data or signal which arrive at the input to an output? Okay? So, for example, in a switch, data which arrives at multiple ports may want to leave through same output port. How it is feasible or implemented. To put this in other words, how do we share an output link between different input links? Okay, the simple way is round-robin fashion, right? First you take data from here to here, then here to here, like this. There are 2 possible approaches: frequency division multiplexing, FDM, and time division multiplexing. Good examples are this. For example, if you take cable TV transmission, okay? So there are many cable TV channels. We may have 100 or 200 channels, but cable is only one cable, one link. But there are 100 channels, and each channel video transmission takes place on a different frequency. So many video contents are transmitted or broadcast at the same time on a single link. That means video content on this channel and this channel, they are multiplexed into a single output or link, okay, in a frequency division multiplexing fashion. Similarly, TDM, the good example of TDM is network switches, Ethernet switch or IP routers, okay, where in a time shared manner or TDM manner, the inputs are multiplexed onto the output. Okay. To illustrate better the FDM and TDM, let's consider 4 users. So let's say user 1, okay, I use different colors, user 1, 2, 3, 4. Okay. First, let's look at FDM. Assume that we have the total link capacity or bandwidth of, let's say, B. Okay. In the case of FDM, just imagine the cable TV transmission. Okay. Data transmission takes place all the time. So the x-axis is the time, y-axis is the frequency. Okay. And all users are transmitting all the time. You can see that, right? But each user is transmitting or using only a small bandwidth, a fraction of bandwidth or frequency band. So this will be B by 4. This will be B by 4. So the total channel bandwidth is B, and there are 4 users. Each user uses up B by 4 bandwidth, and each user transmits data using that B by 4 bandwidth, but all the time. It's not that they are transmitting now, then after some time they are not transmitting now. All the time transmission can take place. So this is, again, a good example is our TV. Okay, all the time video transmission takes place at the same time, but on different frequency bands. Okay. But if you look at TDM, it's slightly different way. So you can see that each user will use up the entire bandwidth B of the link when it is transmitting. But the users are transmitting at different times. Here, each user is transmitting all the time, but on different frequency. But in this case, each user uses up the same entire frequency bandwidth, but they are transmitting at different times. Let's say at time T1, user 1 is transmitting, T2, user 2 is transmitting, then T3, T4. So when a user is transmitting data, he or she is using full bandwidth B. But the user is not transmitting all the time. Each user is transmitting only 25% of the time, according to this illustration. So the effective bandwidth each user will get is 25% of B, that is B by 4. Is that clear? So we focus more on TDM because in the context of this particular course, we study switches and routers. So they all use TDM, not FDM. So we spend more time on TDM. So TDM also, again, there are 2 types of techniques, fixed TDM and statistical TDM. So first, let's look at the key concept here. Again, we consider the same example. Let's say there are 2 input link and 1 output link. Please note that in practice, there could be more than 2 or more than 1. More than 2 input links, more than 1 output link. Okay? So maybe look at this. Assume that these are the 2 input links which is connected to source 1 and source 2, or other switch 1, switch 2, or user 1, user 2. So these are the data sources. Okay? So that is sending data to this multiplexer. Okay? And assume that each link bandwidth or data rate is R bits per second. Okay, as I explained in the previous lecture, the bandwidth and data rate, they are used interchangeably. So when I say R bandwidth here is actually I'm referring to data rate, bits per second. Okay? And you can see that data arrives at different times. Let's say that different slots, for example. So how it works is that first, the data which arrives at during this time slot is sent here. That means the output is assigned to input link 1 at this time, the green. Then it takes data from input link 2, white. Then takes data from green, white, green, white, green, white. Okay? So this is how it alternates. So this is a time division. This is time division, multiplexing. Okay? Assume that each slot duration is T. Each slot duration is T. Okay? and each link bandwidth is R. If we provide the data rate of 2 R bits per second at the output, meaning is that in 1 second, 2 R bits can be transmitted at the output. So at each input, R bits arrive, maximum R bits arrive in 1 second. So in 1 second, R plus R, 2 R bits arrive at the input. And if the output data rate is at least 2 R, then all the bits which are received, the 2 R bits, will be transmitted out on the output link within the same second, within 1 second. Okay, so there is no need for extra buffer and other things here. So in terms of the slots, or slot size, if the slot size here is T, here the slot size will be T by 2. So note that when we say 2 R bits per second, that means there's a transmission hardware here, which can transmit the bits faster. That is twice the rate of the input. So the transmission time is shorter here, T by 2. Okay? So, but how practically it is implemented? We use what is called byte interleaving. So imagine that during this T time unit, 1 byte arrives here. And during this time T, 1 byte arrives here. You take a snapshot, okay, given time instant. Let's say 1 byte is available here. So that byte will be transmitted through the output link. And this byte will be transmitted to the output link within T by 2 time units, because the output rate is twice the input rate. Then it takes 1 byte from here and transmits here. That takes another T by 2 time units. So T by 2 plus T by 2 equal to T. So when it goes back to the first input link, the next byte will be available, because for every T there's a byte available at the input. Is that clear? Again, byte means it's a serial transmission. It should receive bit by bit. 8 bits are received. That's what it means. Then this continues, then green, then white, etc. So in terms of implementation or byte interleaving, this is something like at the output, we have byte 1, byte 2. So these are the frames, data frames, byte 1, byte 2. Okay, each data frame has 2 bytes. And the first byte is taken from here, input link 1. Second byte is taken from input link 2. Then again, first byte is taken from this input. Second byte is taken from the second input. That's how it's implemented. Suppose we multiplex 4 input, then this frame will have 4 bytes. It takes byte 1 from input link 1, byte 2 from input link 2, byte 3, byte 4. That's how it is transmitting. Is that okay? So if you give illustration with some numbers, see, for example, let's say okay, maybe this is what is explained here. By default, when we say time division multiplexing, it is called fixed time division multiplexing. So when you say fixed, it has several meanings. Okay, so they are multiplexed in the fixed order. Okay? Input link 1, 2, then 1, 2, 1, 2 in a round robin fashion. Okay? And also you can think of this as giving fixed and dedicated bandwidth, or reserving fixed bandwidth for each input. What exactly it means? That means if we have 2 input and 1 output, let's say this is R, this is R, this is 2R. Assume that this input is 10 Mbps and this input rate is 10 Mbps. If the output rate is 20 Mbps, what does it mean? Within 1 second, 10 million bits arrive at this input. Within 1 second, 10 million bits arrive at the other input. So within 1 second, 20 million bits arrive at the multiplexer, and all these 20 million bits can be sent out in 1 second because the output rate is faster. Okay? So what we say is that this 20 Mbps is equally shared between the 2 inputs. In other words, we say that out of this 20 Mbps, 10 Mbps is reserved for input 1, 10 Mbps is reserved for input 2. Why I'm saying is because you will come across here in that bandwidth reservation, bandwidth reserved. What exactly it means, bandwidth reserved. Okay, this is what it means. What it says is if 20 million bits arrive at this input in 1 second, these 10 million bits arrive in 1 second at this input. These 10 million bits are guaranteed to be transmitted at the output. So it guarantees 10 Mbps for this input. It guarantees another 10 Mbps for this. So that's why we say that there's a fixed and dedicated bandwidth which is reserved. For each input link, 10 Mbps is reserved at the output. Okay? So from that perspective, it can provide guaranteed service. That is, if you want to transmit some data, okay, you want, let's say, 10 Mbps. So here you get 10 Mbps, here you get 10 Mbps, right? And every link you can get 10 Mbps. You can have guaranteed bandwidth. And also, more importantly, the delay is important. Okay? So delay here is guaranteed. That means if you have many such multiplexers in the form of switches, so these are all switches. Assume that these switches implement multiplexing. Okay? If you send some data here, the source, and let's say this is the destination, can we guarantee delay? Okay, so whether this data from this input to this output can be sent within, let's say, 1 millisecond, within 5 milliseconds. So whether can we guarantee the delay? Yes, we can guarantee the delay. Why? Because it provides fixed TDM, bandwidth is reserved, and there is no queuing delay. That is very important. Why there is no queuing delay? All the bits which are received in 1 second, they are guaranteed to be sent out. So there is no queuing delay. Is that okay? So you go to a shopping mall, there are many cashiers, cash counters, right? Let's say you go to one cash counter. Cash counter is an output, something like that. So cashier is serving the queue, right? Cashier is serving the queue. Let's say for every 15 minutes, 10 customers arrive. So if the cashier, okay, can serve 10 customers in 15 minutes, in the long run, if you look at this, okay, there will not be queuing delay. When people go there and you will get serviced. This is something like, okay, you go to the airport, you go to the counter, service counter, right? The rate at which they service, okay? If you assume that 10 passengers arrive for every 15 minutes, and if the counter person can handle 10 people in 15 minutes, okay, then there will not be queue. There is some kind of guarantee is there, right? So you go to a shopping mall, then you can easily call your friend. Okay, I'm done with shopping, so I will come, maybe I'll just pay and come back. Come, I will start, we will meet, okay? That kind of delay is guaranteed. But you just imagine that there's no guarantee of the service by the cash counter. Let's say it's a promotional period, okay? Or some festival event. There's a long queue at the cash counter. Why there's a long queue at the cash counter? Because the cashier, okay, may not be able to handle. Let's say normally the cashier can handle 10 customers in 15 minutes, but within 15 minutes, let's say 50 customers reach, what will happen? There will be a long queue, correct? And the queue will also build up. If there is more and more demand and the cashier is not able to handle it, then the queue will be more. The queuing delay becomes variable. So if you want to call your friend, you are done with shopping, you cannot guarantee any time. You say that, oh, there is a long queue at the cash counter. I cannot tell when I will make payment, correct? So that depends on the queue servicing and other things. So this is the advantage of fixed time division multiplexing, but it has a drawback or limitation. Bandwidth utilization is not efficient. What do you mean by inefficient bandwidth utilization? Because this terminology you'll come across many times. Terminology is important. Understanding of terminology is also very important, right? So now look at this same case here. Let's say it takes data from the first input green, then white, green, white. Let's say during some period of time, let's say this time, if there is no data available here. Why there is no data available here? Because data is sent by another source. It doesn't mean that the source will be sending data all the time, right? Let's say your computer is connected to the network. Will you be sending data all the time? May not be, correct? Agreed? So if there's no data during this particular slot, what the multiplexer should do? If it is fixed time division multiplexing, this slot is reserved for input 2. If there's no data at input 2, it is reserved, so it will just keep idle. So this, even though the other input has more data, it will not take it. So this slot will be wasted. Is that okay? So if there is no demand at an input, because the slot is reserved, that is wasted. So that's a drawback of any reservation-based systems, right? Let's say these seats are reserved for some people. So if they don't come or come late or something, the seats are wasted. It's not utilized properly. So now, to overcome this limitation, okay, so another method has been proposed that we call it as statistical time division multiplexing. Okay, so this is also called on-demand multiplexing. Now, again, let me give an example. So look at this. Here, first green, then white data is taken from here. But next time, let's say more data is available here, but here there is no data available. So meaning here is that it can take, or the output can be assigned to this input more time. Actually, it should be white. Actually, it should be white, right, if it's a fixed time division multiplexing. But because there's no data here, and this input has more data, it will take it. So that way, it avoids the underutilization problem. Any doubt? Okay. Now let me give an illustrative example. Let's say the input rate is 10 Mbps, here 10 Mbps. Assume that each input is active for 60% of the time. What do you mean by 60% of the time which is active? 10 Mbps means what? In 1 second, this source, maybe this source you can imagine our computer or maybe another switch or another router, okay? So they should be able to transmit 10 million bits per second, 10 million bits in 1 second, right? But this source may not be transmitting all the time. Let's say your computer is connected to the network. You may have 10 Mbps or 100 Mbps adapter, network adapter. So 100 let's say you have 100 Mbps adapter. So when your computer is transmitting, it transmits at the rate of 100 million bits in 1 second. But it's not transmitting all the time, correct? So 60% of the time means within 1 second, so it is transmitting for about 600 milliseconds. So eventually, in 1 second, 6 million bits arrive in 1 second, correct? It produces, even though it's transmitting at the rate of 10 Mbps, it's not transmitting all the time. It's transmitting only 60% of the time. So statistically, or on an average, 6 million bits will be received here. Another 6 million bits will be received here in 1 second. So only 12 million bits on an average, I'm saying on an average. Okay, this is not the maximum or peak. 12 million bits are received at the input. So if we can provide the output data rate, output link of data at 12 Mbps, that is sufficient. That is sufficient, right? Agreed or not? In other words, if you have 20 Mbps link, we can serve 3 10 Mbps. Without any problem, if on an average every input is sending data only 60% of the time. Instead of 2 input, I can serve 3 inputs. So this is an advantage here. Agreed? So if you have a switch, if you have 10 Mbps input, if you receive packets from the link or port at the rate of 10 Mbps, if the output rate is 10 Mbps, still it is possible. Okay? Assume that They are not sending all the time. Maybe 50% of the time only they are sending. So no problem. We can multiplex them. I don't need 2R bits per second. Is that okay? So the links are provisioned based on some average demand or statistics. But now, so because of this, the bandwidth utilization is better. Why? Because with 12 Mbps, I'm able to serve two 10 Mbps. With 20 Mbps, I'm able to serve 3 inputs, each 10 Mbps. But what is the drawback? Okay. It may so happen that, because this example, 6 and 6 is an average, right? But maybe it's a big peak period. Okay, suddenly every user is jumping to connect to the network to do some, to access the internet, okay? So the peak period, each input may send 10 Mbps at the rate of 10 Mbps, right? We assume that 60% on an average, right? Now what happens if each input is transmitting at 10 Mbps, it's active 100% of the time. That can happen, correct? Agreed or not? So you take, for example, the bus on the road. The bus capacity is designed based on maybe the average demand, correct? Frequency and bus capacity and frequency of buses also. Let's forget about the frequency of buses. Let's say the bus capacity is designed based on some average demand because cost and other considerations are there, right? It provides maybe 25 seats, even if it's a double decker, maybe another 25, 30 seats here and there, right? Not more than that. Why they provide only this many seats? Because based on some average demand, some statistics, correct? Now the question is what happens during peak hours in the morning? Okay, if more, let's say there are 25 seats in the bus. If more than 25 passengers, they try to board the bus, what happens? Of course, 25 passengers will get the seat. So if it exceeds 25, they'll start standing, right? So that means there is some buffer. That's a buffer. So when excess passengers reach, okay, the passenger will stand in the bus. But that buffer, the extra space, that's also limited. That's also limited. How many new extra passengers the driver can allow? He will see, okay, the extra space is already full, okay? Then what he will say? He will just simply shut the door. Okay, the bus is full. Even the buffer is also full, right? Don't board it. You wait for, you are rejected. That means you wait for another bus. Is that okay? Similarly here, what happens if each input sends at the rate of 10 million bits per second? That means in 1 second, 10 plus 10 equal to 20 million bits arrives. The total number of bits which reach the multiplexer is 20 million bits. You cannot tell the input that you should not be active more than 60% of the time. That instruction cannot be given. Output is only 12 million bits. You can send out only 12 million bits at the output. So the difference, that 8 million bits is the excessive bits, extra bits. So what will happen to these 8 million bits? So we need a buffer, memory, to store these 8 million bits or equivalently some packets, okay? But the buffer capacity is limited, finite. It's not infinite buffer. So let's say the peak period continues. The input continues to transmit at the rate of 10 Mbps, all the time it's active. So during the first second, 8 million bits will be put in the buffer. During the next second, another 8. So the buffer queue length will become 60 million bits. Then it becomes 24 million, 32 million, 40 million, right? The queue builds up. Like during the promotional period, the queue builds up at the cash counter, right? So what happens? If the queue builds up beyond what the buffer can store, the excessive bits will be dropped. The bits will be dropped. When the bits are dropped, that is the state of congestion. Okay. If the buffer cannot hold in the excessive data, additional bits will be dropped. That's all. There's no other way. Is that clear? So here, there's no service guarantee. We cannot guarantee that, okay, I give you 10 Mbps guarantee or 6 Mbps guarantee and all. So it's based on the demand or some statistics, okay? And there's no guarantee on the delay, okay? Why? Because it depends on the queue. If the load is light, demand is light, the queue may be empty. But if there's more and more demand at the input, the queue will build up. So when the queue build up becomes longer and longer, obviously the delay will be longer, which is a variable. We cannot predict what is the delay. Okay? So that's why the service is not guaranteed, but bandwidth is efficiently utilized. The bus is efficiently utilized. If it is fully packed, all seats are occupied, even the standing, people stand fully, completely used. So it is fully occupied, right? It is efficiently used. When you say fully used or efficiently used, then we need to see, okay, whether the space is used all the time. This statistical multiplexing is used in networks, network switches, Ethernet switch or router. Of course, slowly you will study the topics on switches and routers, okay? And this is also called on-demand time division multiplexing. As I said, the resource sharing or utilization is better, but how actually it is implemented in the packet switches, this is switch or router, is something like this. So here you assume that there are many switches and there are input links. So whenever a packet means this piece of data. Okay? Whenever a packet is received, the packet is stored and put in the queue. Usually this queue is first in, first out queue. And the switch will send the packets one by one to the output link. So we say that if all these packets, they want to go through the same output link, then we say that all these packets, they are contending or competing for the link. Note that there could be multiple output links. So for this example, we don't consider them. Okay? In other words, if, let's say, there are no packets here at this input, that means the output link will service this and this. If this link sends more data, so this input will use the output link, okay, higher fraction of time when compared to other link. It depends on the demand. Whoever has more demand will use the output link more time. Very simple, because we want to utilize the link continuously. As long as there is some buffer or packet here, we want to use it, we want to transmit it. We are not reserving that, okay, first we have to send packet from here, here, here. If it's fixed time division multiplexing, that should go in a round robin, okay? So suppose there is no packet here, then don't send anything here. That doesn't happen here because this is on-demand multiplexing. Again, like the statistical multiplexing example which I gave, if the sum of the input rates, let's say the rate at which the data arrives at each input, if it exceeds the rate at which the output link can transmit, then there will be excess data. Excess data means that will be put in the buffer. So there is a possibility of overflow. When it is overflow, this is the state of congestion. Okay. It may not happen all the time, but there's a small chance that the switch during peak hours, okay, switch or router can be congested, packets may be dropped. That means there's no place in the buffer to keep the incoming packets. Okay. So usually when the packet arrives, there will be interrupt, which will, we are not going into all these details, which will take the packet, store it in the local buffer or queue, etc. Any doubts so far? Next, we move on to the topic on switching. Because here and there we use the term switch. Okay, switch, routers. Router is also a switch. Router is also a switch. This is something like you have RAM and ROM. RAM is random access memory. ROM, read-only memory. That's also a random access memory. Agreed? ROM is also a random access memory. I mean, if you look at the meaning of random access, if you truly, what is the meaning of random access? You can randomly go and pick up any address, you can pick up the data, store or read the data, right? So same thing can happen in ROM as well. But there's a difference. Similarly, switching is a technique, method. Whoever implements it is a switch. Ethernet switch is also a switch. IP router is also a switch. So it's also implementing switching operation. But it does something more, routing and other things, so we give a different name. Right? Similarly, RAM, random access memory, read-only memory. Read-only memory is also a random access memory. But read-only memory, we want to distinguish because you can only read. So we give a different name, right? So what is a switch? A switch has a number of input and output. Let's say the dark color one, these are the input and output. Okay, so you can imagine a small Ethernet switch like a box, and you will have multiple ports through which you can connect using the cables, right? And similarly, you have a large switch as well with multiple line cards and other things. So if you Google it, you can see the nice pictures of a small switch, Ethernet switch, large switch, okay, how a router looks like, okay? So pictorially, we say that there are ports or the links. Port means where you can receive and send data, right? There's a port, even the C port or any port, where you can arrive, you can leave, right? Whether you can receive, you can send, that's a port. Okay? So though we say there are some input ports or output ports, usually every port can act as an input as well as output. You can send data, you can receive data also, right? But many discussions for the purpose of illustration or explanation, I may say this is an input port, this is an output port, so you don't worry about this, okay? Don't get confused. Switching is the process of forwarding data from an input port to an output port, very simple. That means you have an input, some inputs and some outputs. Some data arrives as an input. It should be taken to an output. It's a process of taking or forwarding data which arrives at an input port or a port to another port within the switch. Within the switch. That's very important. It's a functionality within a switch. Of course, there should be a hardware path inside to direct this incoming data to an output port. In addition to that, we need to make a decision. That's also important. When data or piece of data arrives here, where it should be sent? To send to this port or this port? So that decision we need to make. That's also a part of switching. So there are two broad approaches for switching, circuit switching and packet switching. So let me explain the key concepts. First, you understand what is circuit switching and packet switching. Most of the time students get confused, okay? Because once you start reading about another technique, you will start confused, right? But better you get confused. So if you get confused, then there's a chance for you to get it clarified, right? Circuit switching, of course, if you look at the name circuit, everything has a history, okay? We don't have time to discuss all those things. What do you mean by a circuit? Yeah. For electrical or electronics engineers, circuit has a different meaning, right? You have electrical circuit with the resistors and other components. We have electronic circuits with the gates, right? AND gate, OR gate, that's also some electronic circuit, okay? Transistors and other things. So they are circuits. Am I correct? Similarly, for computer science, okay, circuit means cycle. Circuit means it's a cycle. But here circuit has a different meaning. Okay, it's not a cycle or it's not our electrical circuit or anything, right? This circuit name, it has, if I'm not wrong, this follows historically from very old telephony. Maybe if you watch the old black and white movies with the telephone receivers and other things, starting from the analog and the digital telephony, etc. Okay, So let me not go into that, what exactly, why it is called circuit. Okay? But what mean here is that circuit means this. The link bandwidth or capacity is divided into fixed size circuits. Maybe you can imagine that a circuit, okay, corresponds to a fixed amount of bandwidth. So here, in this example, let's say this is one link. You can assume that this link has 4 circuits, or this link bandwidth is divided into 4 small bandwidths. There's no physical division, right? Because how we multiplex, how we take data from the input to the output, that will define, okay, circuit. So already we have studied fixed time division multiplexing, right, where you can dedicate certain bandwidth, right? So here, how switching takes place? It's very simple. You just imagine, okay, it's imagine as an analogy, that within this link there are 4 colored blue, purple, red, green, okay, pink or purple, okay? So there are 4 colored wires. Assume that, please note that there is no such colored wires inside the cable, right? Assume that there are 4 wires inside a link. And similarly, every link has some colored wires. So if we connect, let's say, this blue to this red, if you internally connect, maybe you take another wire, if you connect this blue to red, what will happen? What will happen? All the bits and bytes, whichever arrive at this blue circuit, will leave through red circuit as the output, right? So that means we are not receiving any packets or anything. We are not looking into where is the destination of this data and other things. Okay, very simple. The data, whatever data we receive from this blue, will be sent to this red. So if you assume that we are implementing TDM, so just imagine that these are all time slots, slot 1, slot 2, slot 3, slot 4. This is slot 1, slot 2, slot 3, slot 4. So that means the data, piece of data which arrives at slot 1 at this input will be sent in slot 3 at this output. That's what it means. Okay? In other words, if you have the frame implementation, byte based, let's say byte 1, byte 2, byte 3, byte 4. Let's say at this output, the data frame is byte 1, byte 2, byte 3, byte 4. The blue means the byte 1. First byte, when it is received on this input link, will be sent as the third byte. It takes the position of third byte at the output frame. That's what it means. Okay? Blue circuit is switched to red circuit. I'm trying to explain what do you mean by blue circuit is switched or connected to the red circuit. How is implemented inside? Slot 1, data at slot 1 is sent here at slot 3. Or the first byte received on this is mapped to third byte. Similarly, let's say if the second one here is mapped to the green, that means the second byte B3, B4. The second byte, the second circuit, this will be sent as the fourth byte on this output link. Is that okay? So why we map this blue to this red, why not to others? Maybe because it's a more dynamic implementation, right? Maybe some time ago, some other users or circuits might have used this and this. So when there's a request for connectivity from this input to the output, maybe here only red is available, so the blue is connected to the red. Is that okay? So a good example of this is the telephone network. Of course, SONET, we later touch upon SONET a little bit. Okay, we are not going to study all this SONET and WDM. Okay, SONET and telephone network, they use some kind of TDM, and WDM, they use wavelength. Wavelength switching, wavelength is something like a circuit. Okay. So in telephone network, usually there will be three phases, right? You take, for example, landline or usually telephone. First, you need to set up the circuit. That means you need to dial. Okay, you need to, how do you speak over the phone? First, you need to dial the number of the callee, that is your friend, the other side party, right? So when you dial, have you heard about this term dial? Dial the numbers? Yes? In the context of telephone? What do you mean by dial the numbers? Let's say you want to speak to your friend. First you dial, we say we dial the number, correct? What do you mean by dialing the number? Of course here, nowadays we just press, okay? Let's say you press the numbers, okay? Maybe it may have a historic meaning, dialing the number, okay? Let's not worry about it. So when you press the numbers of your friend, then the telephone connectivity should be established. Meaning is that the circuit will be established in the telephone network, and each circuit will need 64 kbps. The telephone network, okay, the telephone connection goes through multiple switches, that it traverses multiple links. At each link, we need 64 kbps. So one circuit you can imagine is equal to 64 kbps. So 64 kbps reserved bandwidth should be available for this and for this. Then similarly, it is connected to the next switch. So there it will be connected to another output circuit. So once all the circuits are established, setup means at every switch, okay, we instruct that this blue is connected to this red, okay, this purple is connected to this green. So this instruction should be given. That is the circuit setup. Okay. Once you get the ringtone, that means the circuit connection is set up. Now we speak. So whatever we speak, okay, and modern days that is converted into digital, PCM coding and other things. So the data will flow. So whatever we speak, it reaches here, that will leave from here. Right? That is called data transmission. Even in the network also. First you need to set up the circuits. Then you need to transmit data. So whatever data you send on this blue, that will leave through this red. That's all. That's how switching takes place, because we already decided a priori. Once the data, sorry. Once the data transmission is over, the circuit is released. Circuit is released means this blue and the red mapping is removed, so that when a new connection comes, this red may be connected to something else, some other circuit. Because it uses the time division multiplexing, it has the advantage of guaranteed service, and it has a drawback of bandwidth waste, low bandwidth utilization, etc. What do you mean by bandwidth waste? Just imagine 64 kbps is given to for voice transmission. We may not send or we may not speak all the time. There could be a silence period, but still that slot circuit cannot be given to something else. Similarly for data transmission also. So if there's no data arriving at here, the red slot will be wasted. And there is a connection circuit setup time overhead. Let's say we want to send data, very small data, only for 100 milliseconds. If you spend 1 second or 2 seconds to set up the circuits in the whole network, and you send data only for 100 milliseconds, then the overhead due to the setup and release is more, correct? But if you set up the connection, you send a large data for minutes or hours, then that's fine. The overhead is small. Next type is packet switching that implements what is called store and forward technique. Okay? And you can refer slide number 12. So it uses statistical time division multiplexing. Okay? So here the switching is in terms of the packets. So when you say packet, so this is the packet. Packet carries data, few bytes, let's say 1,000 bytes it carries. And it has header, and this has payload. Payload is the actual data. Okay, it's an array of bytes, something like that. And the header includes many information, including the destination address. And if you look at 12, this is how it is implemented. Each packet carries the destination address. When a packet is received, this is stored inside the switch or router. It is store and forward. That means first you need to receive the packet in full. Then the switch will look into the header. Okay, this is the destination address. So if this is the destination address, then this packet should be sent to output 1 or output 2. That's how the forwarding decision is made based on some local table, which you will discuss later, how the tables are built up. So what you need to understand here is that the forwarding decision is based on the packets. It's not based on the circuit. In the previous case, simply said whatever is received on the blue will be sent to the red. Now it is not like that. There is no connection set up or anything. Every packet is treated independently. A packet is received, stored, look into the header, consult some local table, decide where it should go. That is packet switching. So it uses statistical TDM, and it has the advantages of statistical TDM. That is, utilization is high, but there is a possibility of congestion and other things, which we have already seen. And there's also another small problem, like messages may be received out of order. Why? Because let's say you have a large message, very big file. Let's say you are sending or downloading a picture, okay, 10 MB or 100 MB or 20 MB, very nice pictures, high quality, HD quality pictures, right? It's not sent as a single packet. Usually it's divided into multiple packets. Let's say it is divided into 100 packets. So each of these 100 packets are treated independently at the router or the switch. So theoretically, these 100 packets can take their own routes, although practically most of them will take the same route. Okay? So there is a possibility that packet 1 may be received after packet 2. That is possible. So we need extra mechanism, something like TCP, which we will be studying later, which will take care of ordered delivery. Okay, how, even though the network delivers out of order, how the packets are put in the same order will be studied in TCP. Next topic is addressing. So we will not be studying circuit switching. So what we study hereafter is packet switching only. Now, we know that network is used to send data from one end to the other end. That's what we use it for the network. We use the network for some purpose. Let's say host A connected to some local area network. Maybe it's a small enterprise or home or whatever it is. Okay. Let's say host A is connected to local area network X, and host D is connected to local area network Y. Let's say we want to send a piece of data between A to D. Let's say A to D. Okay? How A can send data to D? How A can send data to C? So this is something like postal mail. In postal mail, of course, nowadays we don't use it, right? We communicate through email or other social media, WhatsApp and other things. But usually for placing online order, still we use address, right? So we need to give the address, house address or something, right? So we need an address to deliver correctly. Similarly, each packet needs an address. Suppose A wants to send a message to D. We need an address of D so that A can send it to D. Okay? So there will be the service providers or core networks in between, which will have multiple routers like R1, R2, R3, etc. And the router will make a decision. Okay, this packet is going to D. So then where it should be sent? Should it be sent to router 5 or router 6? So all these decisions need to be made. So we need address. We need some address. Okay. Address here is simply a bit or byte string. So every host, let's say you take our computer or phone or whatever it is, every host which is, or every system connected to the internet has an address, should have an address. And it's basically a byte string. And usually it should be unique. And that address is carried as part of the message. I don't differentiate at this time message, packet, frame, and all. Later we will see the difference between message, packet, and frame. Okay. So it's used for the purpose of routing. What is routing? Routing is not switching. Switching is the function which takes place from an input port to the output port within a switch. Routing is between switches or routers. It's a process of forwarding the message or data to the destination based on its address. That's the routing process. So there are different types of addresses in use. One is the unicast address. So by default, when we say address, it refers to a specific address, specific computer address. Okay. Broadcast, when we say broadcast, when the message or the packet or whatever it carries a specific, some special address, broadcast address, that means that message will be sent to everybody. If it carries unicast address, that will be sent to only one person. Okay, so who has that address? If it's multicast, multicast is a subset of broadcast. Right? Let's say you have EE and CEG students. If I have a message only for EE students, then that's a subset. Okay? If I send a message to all, then it's a broadcast, both EE and CEG. So by default, when we don't mention anything, that refers to unicast address. A host, again just recall, a host means server or computer or even our phone or anything that has an IP address, which is basically a 4-byte IP address. Okay? So I know how you can see your IP address in your device, right? Your phone or computer. You can go to the control panel or settings, you can easily find out. Okay, or if you go to the command prompt, I think ipconfig/all. Okay, or if you use Unix, ifconfig. I forgot about the actual spelling. ipconfig/all if you give using the command prompt. I don't know. You may not be using command prompt all the time. So if you run the command ipconfig/all, it will show. You can try. You can show all kind of addresses. What is your IP address? Okay. What is the MAC address of your device? Okay. And what are the masks? Okay. The mask, subnet mask, gateway address, etc. We will be studying one by one in this course what exactly those addresses are. Okay. So this address is a 4-byte address. This is the notation. Address, let's say something like 192 point something something. Okay. Or let's say 128 point. So you can check your address, IP address. Okay, what is this address? So each letter here refers to a byte, 8-bit. So 0 to 255. Okay, this is an IP address. IP address is a hierarchical address. Hierarchical address is something like our home address. Our home address, so if you look at your house address, okay, it has a street name, block name, unit number, correct? So the postal or courier, okay, or the online shop or whatever it is, how they deliver, because you need to give the address. And some part of the address will tell the street number, some part will tell your building name, okay, or block number, unit number, floor number. So everything should be given, right? So similarly, hierarchical here means this IP address, some bits will represent the network ID. I am not saying how many bits are used here, okay, that you will be studying later because there are different classes of addresses. The number of bits will change. How many bits represent a network ID? So you will be studying in detail later. So I just say that few bits in the IP address will tell the network ID. So every organization like NUS and companies, they have a pool of IP addresses. So this pool of IP addresses belong to NUS. So if you look at the IP address, you can tell this is NUS address. This is maybe Singtel, or every ISP has a set of addresses. Okay, every organization has a pool of addresses. Okay? But we cannot remember the IP address. Let's say you are using a remote server, okay, Gmail server or the NUS server or anything, any address, okay, you don't remember the IP address of the addresses. It's very difficult, right? So usually we give the ASCII name, .nus.edu.sg, right? And at Gmail, something like that, right? So this ASCII name can be translated into the host IP address by means of DNS. So if you try to access a website, you just specify the ASCII name. You don't specify the IP address, right? Of course, if you know the IP address, you can specify the IP address also, right? But usually we don't. So initially there will be DNS, domain name system, which how it works. I don't know whether you'll be studying in this course. Maybe you'll be studying in, there's another network course, network protocols and applications. There you may be studying. But DNS will help you translate the ASCII address into IP address. That's what you need to remember. Okay. In addition to the IP address, every host has a hardware that's called network adapter or network interface card within your system. So this network interface card or network adapter, okay, that only connects using the cable or something to the wireless adapter or wired adapter or whatever it is, which is used to connect our system to the network. Okay. And that hardware adapter, it has an address associated with that. That is the 6-byte Ethernet address or MAC address or hardware address. Maybe in general it's a hardware address. Okay. And the format is 6-byte, which is usually used A:B:C, etc. Or sometimes you see A-B. Okay, so this is the hardware address you have. So usually we have two types of addresses. A host has two addresses, IP address, hardware address. Why we need two addresses? That's a good question. So you will understand later, okay? IP address is a hierarchical address which is used for routing purpose. Because when you send some data, let's say you try to access from the remote website, the data has come to your NUS network. By looking at the address, okay, all the routers and everything, they will understand this is an NUS network. So that will be forwarded here. This is something like a postal delivery, okay? But once it reaches the final network, could be a broadcast network like this. Let's say this is one network. Okay. Or it could be connected to a switch, Ethernet switch or whatever it is. We say that all these hosts belong to one network. Okay. Then we need to decide, so this router, okay, has to decide whether this particular message is meant for this or this or this. Right? This is something like in your house. House has an address, right? Let's say 4 people are staying there. All 4 people will use the same address, like an IP address. But these 4 people have different name, right? So once your postal mail or anything or courier packet or whatever it is delivered to your mailbox, that item may belong to any one of these 4, correct? Who it belongs to, then we need to look into the name. Okay, the name or the ID or whatever it is, there should be some unique name, correct? Then they decide, okay, 4 people are staying here, but this carries this name, so it belongs to you. That's all. So similarly, until this router or this router, let's say A is sending to D, until the packet reaches router 8, IP address will be used. Then it has, this is something like a single house. All these users use the same IP address, but they have different name, different hardware address. And this will deliver to D or E or F based on the hardware address. Okay? And note that IP address can change. That is, you have a computer now you connect to the NUS network. Then evening you go home, you connect to some other network, your IP address will change. You can go and check the IP address. Right? Today night you fly to another country, you want to fly to your home country, you connect to some other network, your IP address will change. But your hardware address will never change. This is something like your name doesn't change. You can move one house to another house. Right? You can move from one house to another house. House address is the same. Your name is the same, but you are moving from one house address to another house address. So you can attach your system to one IP address to another IP address. But your hardware address should remain the same. Okay, now we are going to look at two examples. So before we look at the example, let's look at something more on the MAC address or hardware address. Hardware address is non-hierarchical. You cannot decide based on the hardware address it belongs to Singapore or NUS or this country or this university and all. Right? It is manufacturer dependent. Okay? But of course, some bits may represent the manufacturer who manufactured it. Let's not go into that because that doesn't help us for routing or anything. Like our credit card, some bits will tell whether it's a Visa or this, Masters or this, that. Right? And what is another thing, what is more important to note here is this. All these hosts which are connected to the same network means all the hosts which are under the same router interface. There is a router, there's a router interface or router port to which there's a network. It could be a broadcast network or it could be Ethernet switch-based network. There's a network, it's a single network. So all these hosts will have same ID in IP address. If you look at the IP addresses of all, let's say you are all connected to the same network, then if you look at the IP addresses, some bits will be the same for everyone. That represents the network identifier. Okay, this helps for routing. Okay, then how, let's say router 8 receives a packet, how it decides whether it should go to D or E or F. So every host has address resolution protocol ARP table. ARP table has two entries, IP address and hardware address. So each host and each router interface, because router may have more than one link, here 1, 2, 3. So each link has an IP address and hardware address. So each host has a table of IP address and the corresponding hardware address of every host and the router connected to the network. How they know this table? There's a protocol which is called address resolution ARP, I think which you will study in second part. That protocol will be running, okay, periodically, and that will get to know the addresses. Okay? This has, yes? The 6-byte Ethernet address is fixed for your hardware. It is fixed. It is hardwired. That's why it's called hardware address. It's hardware. You cannot change by software or configuration. Okay? That means, that's why I said, you use ipconfig command or code to control panel, etc. You try to see your IP address and MAC address. Your MAC address will be the same whether you are here or at home or anywhere. Your computer will show the same MAC address, but IP address will change. Any device which is connected to the internet. That's why you take your phone or router or anything, there will be a MAC address, right? MAC address. That's a hardware address, right? You can see what's your MAC address in your phone and other things. I mean, there you may have wireless MAC. If it's a wireless, if you connect by wireless means, it's a wireless adapter or wireless MAC. It could be a wired address as well if you have wired connectivity. So there should be a hardware address. But there should be ARP running in every network. But first of all, you should know what is a network. This is very important. Okay, a network is all the hosts connected to the same router interface. You see, this is a router, this is one of the interface, one port. Though we say by a link as a broadcast, it need not be a broadcast. Okay, it can be a bus or hub, both are broadcast network, or it can be a switch also. Here it can be Ethernet switch also, but they are all connected to the same router port. So this is a single network. They all use the same network number, network ID. Let's look at an example. Host A wants to send a packet to host D. Again, I use the term packet, message, this loosely, okay, but it has a meaning. I may use interchangeably, let's not worry about it, okay. At this stage, let's not worry about it. Later, we will worry about the terminologies. So what will happen? Okay. Host A wants to send it to host B, and it has to prepare the packet. Actually, it's a frame with two addresses. So this is IP address, and this is the hardware or MAC address. Okay, so each packet, actually it's a frame, okay, that has two addresses. That message should carry IP address and the hardware address. Okay, so ideally we should carry IP address of D, the destination D, and the IP address of, hardware address of D. But host A cannot know the hardware address of D. Okay, because in the world, millions or billions of devices can be there. Every host cannot know what is the hardware address of every other device in the world, right? That doesn't know, okay? But what it knows is IP address. How it knows the IP address? It uses domain name system, DNS. Okay, let's say it wants to send it to D. It knows the send or receive or whatever it is. Let's say you have the ASCII address .www dot this some name. So first it tries to get the equivalent or the corresponding IP address using DNS. It will automatically use DNS and get the IP address. Okay? If it is not existing, there will be DNS failure. Sometime you might have noticed, if you give a wrong address or something, DNS cannot find it. So this IP address will be D. When it gets IP address, what it does is it compares the network identifier part of its own IP address and the IP address of D. Because they are connected to two different routers, or they belong to two different networks, the network identifier of A and network identifier of D will be different. So A will understand that D is not part of this network, D is part of some other network. So when it is a part of some other network, it needs routing. It needs routing, it cannot directly deliver. This is something like in the house, we have 4 people. Okay, I want to send something to another friend who is staying in the same house. I don't need to do routing. I'll go and knock the door and I can forward it. Okay, I know this fellow is here. I want to send this message to him. Okay, but if I know that I want to send something which does not belong to my address, then maybe I need to do routing, maybe through post office and other things. Okay. Then what is the hardware address it will write, the destination hardware address? Because it doesn't know the hardware address of D, it will write the hardware address of R0. R0, not exactly R0, this interface, each interface of this router or each port of this router has an interface, an address. So this address will be written here. Then what it does, this frame or packet is sent to this network. If it's a broadcast network, it's broadcast, or if it's a switch network, it will be forwarded within the switch network. So assume that it's a broadcast network, okay? So when this frame is sent to this local area network X, everybody will check this address, the hardware or MAC address. B can see that, C can see that, but they know that this hardware address does not belong to itself. So only this router 0, when it gets this frame, it understands that its own address matches with the hardware address which is carried in that message. So it will grab it. It will copy it. When it copies it, then it looks into the destination IP address. Then it will forward it this way. Then it will forward to the next router. So based on the IP address, destination IP address, every router will forward it, route it. Finally, it will reach R8. Which route it will choose based on some routing algorithm, you will be studying later. I'm trying to give what's happening at a high level, okay? Until it reaches R8, the destination IP address will remain the same. But the hardware address will change at every link. Whenever you send to another system, the hardware address will change. But the IP address is the final IP address, D. Once it reaches R8, R8 looks into the IP address and it finds that this IP address, the network number, the few bits network number of this IP address matches with the network number of this IP address. Okay, because this R8 has two interfaces. This is one interface that has an IP address. So the ID of this IP address and this ID will match. Then R8 will understand that this packet should be delivered to this network. So it will not do further routing, but what it will do is this R8 will prepare the packet where the IP address is D and the hardware address will be D. Because this router, based on the ARP table, that knows if this is the IP address of D, what is the corresponding hardware address? That is known to the router. So router will insert hardware address of D here. Please note that hardware address of D is known to A, not known to A, but it's known to this router. So when this is sent to this network, multiple hosts can receive it. D can receive, E can receive, F can receive, but only one will accept. D will accept it. Because only D address matches with this destination address. Any doubt? Students, any doubt? Now let's look at a simpler example, packet transfer example 2. Now host A wants to send a packet or a piece of message to host C on the same network, LAN X. You can see A and C, both are in the same network. So the first step, host A will get the IP address of host C using DNS. That's the first step. It obtained IP address of host C using DNS and it is attached. So this is the IP address and this is the hardware address. So it will write C, IP address of C in this field here. Now it compares the network ID part of A IP address and that of C IP address. Because they belong to the same network, the network identifier will be the same. So it understands that this is in the same network. So it will directly write the hardware address of C in the hardware address field. Why it is possible? Because it knows the hardware address of C from the ARP table, which it maintains. You can also see the ARP cache in your system. You can Google it, find out how to find the ARP cache in your system. You can easily check. This is the ARP table. So you can see basically the hardware address and IP address, okay, of those hosts which are connected to the same network. Any doubt? So let's move on to the next topic. Of course, there is no break, but I have tried to end the lesson early, correct? How we are going to measure the performance. So when we transfer data from one end to the other end, let's say it goes through switches or routers, okay? Yes? Yes? Please be louder. Yes. Okay, that's good. So that's a routing problem. Like when it receives packet R0, of course here there's only, in this example there's only one link, so it sends to R3, right? Something like you are sending to the service provider. But here you have multiple chances. It can go through this way or this way. Of course, there could be other networks also. I have not shown here, okay? So there are multiple routes from R3 to R8. There are multiple ways to reach. That's your question, right? So which route we will use? That is based on, there's a forwarding table. Each router maintains a forwarding table, okay? That forwarding table tells, okay, this is the forwarding table. So this is the network ID, okay? And what is the next hop? If it receives a packet, let's say this is the network ID of that packet, let's say it belongs to NUS, okay? Where it should go next? Should it go to, let's say, R3 or R1, okay? That information is available at the forwarding table. Each router has a forwarding table. So whenever a packet is received, it looks into the network ID, okay? Then it decides where it should go. Now the next question is how we build this table. Okay, so there are routing algorithms. Okay? There are two popular routing algorithms, link state and distance vector based routing algorithms. So this routing algorithm will be periodically running within a network. Okay? And they all choose what is the shortest path or minimum cost path to reach the destination. Okay? So based on an algorithm, routing algorithm, those two routing algorithms you will be studying in part 2 of this course. Okay? And based on this routing algorithm, the routing table or forwarding tables are built. And these forwarding tables are available at each router. So whenever a packet arrives, it looks into the destination address and it looks into the network ID of the destination address. Okay, this belongs to NUS. Then it consults the local forwarding table and decides what is the next hop, whether it is R3 or R2. So that information is written here. Okay? Because I'm not going into how the routing algorithm works here, so that you will study later. Now we are going to look at a simple formula to measure the performance of the transfer. Because later we will be studying some protocols, you should be able to understand how good is the protocol, how we say this protocol is good or bad, okay, how effective, what is the efficiency, okay, what is the bandwidth utilization, etc. We use normally two metrics, delay and throughput. Okay, that means if, let's consider maybe a simplicity one link. Of course, you can extend the formula or definition to multiple links, okay, on a path. So if A and B are connected by a link, let's say you want to send a message which has certain number of bits that has size. Let's say I want to send 10 MB. This is my message. I want to send from one end to the other end. How much time it takes? Let's say I want to download an image from a remote server. It could be social media, okay, or maybe email or somewhere, right? So let's say I want to download a large game, okay, game file, 50 GB, 100 GB game, okay, I want to download into my console. How much time I need? Okay? So that is very, how do I measure? Okay, that's important, how much time it will take. And also I will be interested to know the throughput. Throughput is also important. See, for example, let's say at our home, let's say I have 1 Gbps connection. Okay, this is very common nowadays in Singapore, right? I have 1 Gbps fiber broadband connection. But note that this is only a last mile or first mile. This is the only one link. Your data should traverse multiple links, multiple routers. Okay? So, but ideally, what would we expect is if I have 1 Gbps link, let's say I want to download, and let's say maybe a game, I want to download a game which has 10 gigabits. Okay, usually we use bytes, but to make calculation quickly, I put in bits. Let's say I have a file, game file, or maybe a HT movie. Okay, I want to download from a remote server. Okay, the capacity or the size of the movie or the game is 10 gigabits. I have a link capacity 1 gigabits per second. So how much time it will take to download that file? Yes, is my question clear? I have a link whose bandwidth or capacity or data rate is 1 Gbps. 1 Gbps means 1 gigabits per second, which I can receive or transmit, right? So how much time it will take to transfer 10 gigabits file using 1 Gbps link? Yes? Yes? Please be louder. Very simple, right? But I don't hear anything. 10 seconds. Okay, good. Just 1 second, we should be able to transfer 1 gigabits per second, right? But when you try to download such 10 GB movie file or this at home, most of the time, or almost all the time, you will not be able to transfer within 10 seconds, right? It may take minutes, 10 minutes also sometimes, right? So 1 Gbps is the bandwidth which you have, bandwidth of the link or data rate of the link, okay, which is provided to you. But what you measure, what you get is not this 1 Gbps, okay? Instead of 20 seconds, okay, it may take, let's say, 50 seconds. We think that ideally within 10 seconds I should be able to download it, but it's not happening. Let's say it took 50 seconds to download, right? Then I need another metric to specify, okay, how good is my transfer. That is the throughput. That's the throughput. That is how number of bits transferred per unit time. That means if we need 10 G bits, if you transfer 10 gigabits in 50 seconds time, this will be 0.2 gigabits per second. That means the bandwidth which I have is 1 Gbps, but the throughput or effective throughput what I get is only 0.2 Gbps. 0.2 Gbps is 200 Mbps. 200 Mbps, right? So this is the throughput. So I need another metric, okay? So bandwidth is a parameter which is provided to us. This is the link which I have, but this is what I get. Bandwidth, data rate, and capacity, as we discussed in the previous lecture, they can be used interchangeably. I'm not going into the details of the definition. Data rate, okay, to recall, it's a rate at which bits are sent. How many bits can be sent or received in 1 second? That is the data rate. And we use this notation for our course, and most of the books also follow that. Okay, don't get confused with the notation. When I say 1 kbps bandwidth, I use base 10. That refers to 1000 bits per second. Similarly, when we say 1 Mbps, it refers to 10 power 6. 1 Gbps, 10 power 9. 1 Tbps, terabyte, 10 raised to the power 12. So this is the notation which I am following, okay, which we are following. Many books also follow that. But if you take the throughput or effective throughput, which we say number of bits transferred per unit time, okay, mathematically it's the ratio between the message size and message transfer time. What is the size of the message? What is the size of the transfer time? But for message size, usually we use base 2. If I say 1 kilobytes, I'm transferring 1 kilobytes, it's not 1000 bytes. It is 2 raised to the power 10, that is 1024. If you say the message size is 1 MB, that's not 10 power 6. It is 2 raised to the power 20. That is 1024 multiplied by 1024. Similarly, 1 GB is not 10 raised to the power 9, but it is 2 raised to the power 30. We use base 2 for size. Whether it is the size of the memory, size of the file, size of the image, size of your hard disk, size of your SSD, size of whatever it is, any size, we use base 2. Why we use base 2? That has historical reason. Let me not spend time on that, right? If you're curious, you try. Of course, I'm not going to ask questions like this, why we are using base 2, okay? Maybe another 5 minutes. I'll try to finish this quickly. So how we are measuring message transfer time? So 1 or 2 slides we see before we wrap up today. Assume that we are given a message of some size expressed in bits. If you are given in bytes, you convert it into bits. Okay? How long it takes to transfer the message from one node to another node? When we say a node, that's a system. Okay, host or computer, switch, router, router to router, router to switch, switch to switch, host to host, host to switch, a link which connects to system. System is a node. Maybe because usually we draw a graph to represent the network and all. From that graph theory perspective, we call it as a node. Those who studied graph theory or data structures or something should be knowing it. Okay? And we can also define message transfer time over one link or on a path which traverses multiple links. Here we will study transfer for one link. Maybe in tutorial we discuss how to calculate the transfer time over a path, etc. And there are many delay components which are introduced. Transmission time or transmission delay, how long it takes for a message to be transmitted, and propagation delay, queuing delay. These are some delay components which are more interested. And there are also other delay components like processing time, packetization delay, etc. Processing time means when a packet is received. Processing time means when a packet is received, it should be stored, it should be processed. That means we need to look up the local forwarding table to make some decision. Some processing is done where it should go, correct? And this processing time is mostly the same for every packet. It's independent of any protocol or something. Similarly, packetization delay, how much time it takes to generate a packet at the source. That's the packetization delay. So those are not of much interest to us because for different scenarios, this will be the same, remain the same. But what the transmission time, propagation time, queuing time will change depending on the scenarios. So we are more interested in these delay components. So let's look at the definition of this message transfer and the delay components. So let's start with transmission time. Assume that A and B are connected by a link. So we have a message with certain number of bits, so size number of bits. We want to transfer from A to B. Transmission time, the terminology is very important, is the time to transmit message bits onto the link. Note that there is a transmission hardware here, this is similarly transmission receiver hardware here. When you say message is transmitted, it won't transmit at once like this, or it won't transmit byte by byte. It's a serial transmission, bit by bit only transmitted. So there's a transmission hardware here that will transmit bit 1, bit 2, bit 3, bit 4, bit 5. One by one it will transmit. Okay? So it takes some time to transmit one bit. Equivalently, it has to drive the signal for every bit. Okay? So how much time it takes to transmit size bits? That is the transmission time. is the time elapsed between the beginning of transmission of the first bit and the end of the transmission of the last bit. If you want to transmit 1000 bits, okay, you start your timer. Okay, first bit is now being transmitted. Just we start transmitting the first bit, then you stop the timer when the 1000 bit is transmitted. So that time will give the transmission time. Okay, and the definition mathematically we can say it's size by bandwidth. Is that correct? How much time we need to transmit one bit? That is 1 divided by bandwidth, right? Bandwidth or data rate is the number of bits that can be transmitted in 1 second. So 1 divided by bandwidth is bit transmission time, the time required to transmit one bit. So to transmit size number of bits, it is size divided by bandwidth. So message size divided by bandwidth will give the transmission time. And note that transmission means when A transmits, the bit is here. Don't think that when A transmits immediately, it will be at the other side. No. It's something like a pipe. Okay, something like a pipe. Let's say you have a basket of balls. Each ball is a bit. You want to transfer this basket of balls through this pipe. So what? Okay, let's say you are allowed to pick up ball one by one. So I pick up ball number 1, put it on the pipe. Then ball number 2, ball number 3, ball number 4, ball number 5. Okay. So this ball, when I transmit, I put it at one end of the pipe. And this ball should travel or roll to reach the other side. So it takes some time to travel, okay, to reach the other side. That traveling time is the propagation time. Traveling time is the propagation time. So you can define it for a bit. The time to traverse from A to B, which is nothing but distance divided by speed. Okay, it depends on the propagation speed of the link. It depends on the medium. Usually in the medium it is, the ideal case is 10 raised to the power 8 meter per second. Do you remember this? From the school you might have studied this speed. Okay, ideal speed in the free space, etc. But practically within the medium of the cable, we get 2 raised to the power 10 power 8 meter per second, approximately 5 microsecond per kilometer. It takes 5 microseconds to travel 1 kilometer. That's how it works. Okay? Now, there's a queuing time, how long the message is waiting. Let's say a message is ready at A, but the output link is not ready. It's transmitting something else. So it has to wait for some time. That is the queuing time. But how long it has to wait, it depends on the demand. How many other messages are queued up here, right? So it's a variable. The total time is TT, transmission time, plus propagation time, plus queuing time. That's the time required to transfer. How we define this? TT is the time when the last bit is transmitted here, right? A transmits first bit, second bit, third bit, fourth bit. At time TT, the last bit is transmitted. And when the last bit is transmitted, the previous bits were traveling here. But look at the last bit. The last bit it will take another TP time units to travel to reach the other side. So TT plus TP will be the time when the transfer is complete. Okay, it's a one-way unacknowledged transfer because we say that the transfer is complete when the bit is reached there. We are not dealing with the acknowledgement here. This is the last slide. Let's look at today before we wrap up. The same thing I explained maybe in a slightly different way. Let's say we have A and B. There's a link. And let's say T1 is the time when the message is ready at A. Message is ready for transmission. The message is ready. The packet has already arrived. But A may have some queue. It may be transmitting the previous packets before it takes up this. So let's say T2 is the time when the first bit of the message starts transmission at A. That means T2 minus T1 is the queuing time. Right? T1 is the time when the message is ready, but T2 is the time when it starts its transmission. Let's say T3 is the time when the last bit of the message is transmitted. Because T2 is the time when the first bit is transmitted, T3 minus T2 will give the message transmission time, the time required to transmit the message. Let's say T4 is the time when the last bit reaches B. Since the last bit was transmitted at T3, at T4 it reaches B. T4 minus T1 will be the message transfer time. Now when you add all of them, queuing time, message transmission time, and propagation time, that you will get the message transfer time, right? So that will be, when you add all of them, T2 minus T2 will get cancelled. T3 minus T3 will get cancelled. Then you will have only T4 minus T1. T4 minus T1. T4 is the time when the last bit is received. T1 is the time when the message is ready for transmission. So when you add all these things, queuing time, transmission time, propagation time, you will get the message transfer time. Okay? If nothing is specified or you cannot know about the load, maybe queuing time can be ignored. It depends on the problem context. Okay? In that case, it will be simply transmission time plus propagation time. Okay, let me stop here. It's already 11:40. I don't want to take much of your time. So any doubts? If you have any doubts, those who have doubts can stay here. I can spend more time. Others may please leave.